Hello everyone, this is Dr. Hopkins with more good news. We're going to continue discussing buffers. So remember, our definition of a buffer is basically a solution that's resistant to changes in pH. But there's nothing particularly special about a buffer. They're mostly just very practical solutions that you would make in the lab, where in a case where you wanted to run an experiment or use something in the clinic where you needed to control the pH of a solution. So you would have to make a buffer. Okay, so I have an example here of, if you wanted to mimic the conditions in blood, you need to have your pH be controlled at around 7.4. So let's learn how to make buffers because they're very practical. We want to learn how to do this. So what do we need to consider? The first thing you need to consider, absolutely, is what's your desired pH. If you want to hold a pH of 3, it doesn't do you any good to make a pH 9 buffer. Okay, so once you figure out your desired pH, you need to pick an appropriate weak acid conjugate base pairing. So in other words, how do you do that? You look at their Ka or their pKa, the negative log of that, and if the pKa is close to the pH you want to hold, and actually as long as the pKa is within 1 from the pH that you want to hold, you've got a good buffer system. So if we consider our acetic acid acetate system that we've been dealing with, the buffer we were dealing with in the last video, the pKa was 4.74, so that would be a range from 3.74 to 5.74. So if you wanted a pH 4 buffer, it works. You want a pH 5 buffer, it works. We'll get into this a little bit more. You'll also have the conjugate acid base pairs of multiprotics. Remember, they might have 2 or 3 of them. Each one of them would be a different buffer. So here I show the Ka2 for phosphoric acid is 6.2 times 10 to the minus 8. The pKa is then 7.2. So if you wanted to hold something at a pH of, like the example of 7.4, you could use this phosphate, this conjugate acid base pair for phosphate. All right, the next thing you need, so once you have your pH, you need to figure out, what are you buffering? What's going to add to it? How much acid or base is going to potentially be added to this so you can make sure that your buffer holds the pH constant? And so the first thing we're going to talk about is this idea of the buffer concentration. So you need to pick an appropriate buffer concentration. And when we talk about buffer concentration, we actually mean the sum of the molar concentration of acid and the molar concentration of the conjugate base. So when we say, well, we want a 0.5 molar buffer, that's the total of acid and the conjugate base. So as an example, we'll pick on the acetic acid acetate we've been working with. So remember, we made one that was 0.167 molar acetic acid, 0.167 molar acetate. Those are the two concentrations of each of the components, but the buffer concentration is then the sum of that 0.334. And you also, and it's kind of a side note, when you talk about a buffer, you name it based on the conjugate base. So this is an acetate buffer, or you might have a phosphate buffer or something like that. So you don't typically say it's an acetic acid buffer. And then that concentration factors in what we were talking about is this idea of how much acid or base do you think is going to be added to it. It says you need to consider the buffer capacity of your buffer. So in other words, how much acid can be added or base can be added to that buffer before the pH changes maybe greater than 1 pH unit. And so this is basically a calculation of, hey, how many moles of my acid do I have in my solution versus the number of moles of base is likely to end up in my solution, or how many moles of conjugate base do I have in my solution versus the number of moles of acid that are added to it. We will look at this, we will explore this idea of buffer capacity quantitatively a little bit later, because right now we still don't know how to make a buffer. We're just considering the factors that we would need to do. Okay, so now let's make our buffer. So we need to know what our buffer is and what our buffer concentration is, the two principles we just talked about. And then at that point, once we know our concentration, we know our buffer, we use the Henderson-Hasselbalch equation to determine the individual concentrations. And then we're going to make it one of three different ways. Okay, so the most obvious, most people look at it and say, well, I've calculated the acid and I've calculated the base concentration, so just add the concentrations of acid and base to the right amounts. And that is one way to do it. But it turns out there may be easier ways to do it. So you could start with, say, the weak acid. So just add all weak acid and then just add a strong base to it. So you actually react it to make the conjugate base until you have the correct pH. And conversely, you can start with the conjugate base and add strong acid until you get the appropriate concentrations where the pH is correct. Those last two are, it's similar to the first one. They're a little more difficult to do in the lecture. In the lab, you're going to see that they're very easy to do. Okay, so let's go through the process, or at least let's start the process. Let's make 100 milliliters of a 0.1 molar, okay, that's our total buffer concentration, of a pH 5 acetate buffer. So that would be how the language would be written for how to figure out what your buffer is. So let's determine the concentrations of acetic acid and acetate that we need. So here we have set up part of the problem. So we've got our concentration is 0.1. That's our total buffer concentration. And I've written it out as the sum of the two components. And then I've written the Henderson-Hasselbalch equation in a general form. So we want a pH 5 buffer, so 5.0. The pKa of this, if you remember, is 4.74. And then this is plus the log. Now what do we add in this part? Okay, so what we're going to do is we've got 0.1 is our total, so 0.1, and then I'm going to set and it doesn't really matter which one, but I'm going to set that equal to x, because this is just going to be an algebra problem. We have the total, we can figure this out. So we have x is our acetate concentration plus 0.1 minus x, right? Because this would then be 0.1 minus x, and if you sum that up, that all equals to x. So that means this is the log of x over 0.1 minus x. Okay, so then if we do this subtraction, so we'll skip over this. So this is 0.26 equals the log of x over 0.1 minus x. Okay, now how do we remove a 10 base log? We would do to the 10th power. So 10 to the 0.26 equals 10 to the, and then that removes that, equals x over 0.1 minus x, so 1.82 equals x over 0.1 minus x. And there's our math, and we set this up and solve for x, which I'm not going to do all of the algebra at this point, but it ends up being basically 2.82x equals 0.182. And so x is equal to 0.0645, and 0.1 minus x equals 0.0355. Those are our concentrations. So that, because I set x as my base, is C2H3O, it's O2, excuse me, minus, and that is equal to my acid concentration. So those are my two concentrations that I need in order to get a pH 5 buffer totaling 0.1 molar overall. And it's a good idea to actually check. You'll notice, so the pKa, so our pH 5, we want something that's a little higher than our pKa. That means it's a little more basic. So we're going to end up with more base than we have acid, and we do. We have almost twice as much base as we do acid in this buffer case. Now that we've learned how to set up a buffer, these are the key takeaways from this video. We have the fact that we've learned that buffers are useful. The concentration is the total concentration of the acid plus the base. The capacity of it is its ability to maintain pH based on however many moles of acid or base we add to it. And then we've learned how to use the Henderson-Hasselbalch equation to determine the concentrations. So until next time.